Dub South, Wildcat. Yeah, yeah, yeah. Okay. Murphy. Let's go. Let's go. In the place with his homies.
Alright, well, welcome back, Algebra 1 students. So that was what was supposed to be played at the beginning of the last video. I realized I didn't have the sound up properly. But there you go. We are graphing. We are definitely graphing in this chapter. We're graphing our quadratic functions. And the last section we were just looking at the ax squared, and now you can see we adding c. So we're actually going to add c, and then eventually the next one we'll be seeing adding b, which would be a middle term, a bx term in the middle. That'll be our next lesson. So we're just building one step at a time as we keep going on, learning about how to graph these quadratic functions. So let's go on into our cartoon first. So here's a car with a bunch of dogs. Looks like they're joyriding in the neighborhood. It says, careening through the neighborhood with reckless abandon, none of them suspected that Tuffy was still tied up. You can just hear the as he gets choked as he's still tied up to wherever he was, his doghouse or something. Alright, let's move into our graphing core concept here on page 252 there in your notes. We're looking at this core concept, and you can see on the picture over here, remember we're looking at these U-shaped graphs. They are called parabolas. Remember that from last lesson. We can call these parabolas. And our parent function would be the blue one right here. This is our parent function. I wrote that down there. You want to put that also there maybe to show that when it's c is equal to 0, if this was 0, and we just have an x squared only, this is going to be our parent function right here. And it would actually be, if it's only x squared, it's what's the parent function. So really, I should put down that the parent function is when it is equal to just x squared. So if it's just x squared, that's our parent function. If there's a number in front of it, like we saw last time, we could have an a number, then that's not our parent function. That would have changed from our parent function a little bit. We call that a transformation, and we talked about the vertical stretching and vertical shrinking that number could do it with. If it's a negative, we talked about that in the last lesson as well. If it's a negative, that would be a reflection. It would flip over the x-axis, now it would be opening down. So remember, when that a number is negative, it could just be a negative, like a -1. It's going to flip it. If it's positive, it stays opening up. If this a number is something other than 1, then it's going to either stretch it or shrink it. If it's bigger, if it gets bigger than 1, like 2, 4, and so on, then it's going to stretch. It's going to stretch it. It's going to get narrower and thinner. If this a number is between 0 and 1, like a 1/2, a 1/3, a 1/4, a 1/5, something like that, anything that's between 2/5, 2/3, it's going to make it wider. It's going to get closer to the x-axis. I did want to look at the graphing calculator just to show you that real quick. I think that would be helpful to see. So if I just put my parent function in here, just the x squared, as you can see, there it is. So there's our parent function. And if I just now look at, what if I add a c number to this? And if you notice on here, when we add a c number, what happens? If you add it, if you actually say c is greater than 0, so it's going to actually be plus c, it's going to move, it's going to just shift it up. It's going to move it up. If it's going to be less than 0, so it's like minus some number, the c is a negative number, and it's minus something, then it's going to move it down. That's what's going to happen. Let's take a look at see how it would work here if I just put the x squared again. So there's our parent function, but then I said, let's say plus 2. So you can see it moved it up. All it did, it moved it up. It stayed the same shape, but it moved it up. If I said over here, I put my x squared again, and I say, let's say minus 2. Minus 2, if it's a negative, it's going to move it down. It's just going to shift it down. That's all it's going to do. Now, if we have an a number, remember, so let's say if I put a number in front of this one, if I give it an a number, let's say 3, you can see what it does there. It makes it narrower or thinner on the graph. If we give it a let's say a fraction instead. So let's say if I go back to my regular parent function shape, so these are all in the parent function shape with just an x squared. But right now what we see here with the black one and the red one, these are shifting up or shifting down. And we're going to call that a translation. I'll show you that here in a minute. But let's see if I put this as a 1, maybe a 1/3, 1 divided by 3, you can see now it gets wider. Remember, it's getting wider there. If you put a negative in front, let's say if I put a negative in front of this one, just a minus sign, you can see how it flips it down. The negative in front of the x squared term flips it down. So if that beginning term, that leading term with the x squared term, if that's negative, it's going to be opening down. All right, let's move back to looking at our core concept. So just right here, what do we say when we're talking about the translations? We already talked about, the A number, and what we would say there was stretching or shrinking or reflection in the x-axis if it is a negative. Well, with the ones here, for the green one that's going to be going up, this is going to be a vertical translation, C units up. That's what we would say. If on the red one, if it's moving down, we would say it's a vertical translation, C units down of this graph. So C units down. Don't need it on the of. So you can highlight those things right there. That's what we're going to say for this. And it's the absolute value of C, so it doesn't matter if this is a negative, you're just going to say the number. You're not going to say a negative C units or something like that. It's just whatever the C is. And then what about the vertex of these? So here's another thing we can notice is that the vertex, right here, our vertex is 0, C. So the x is 0 because it's still right here on the y-axis, but the number now is shifted up or down. So your vertex is now going to be 0, C. The axis of symmetry is still going to be x equals 0. Because the axis of symmetry is that line that's going to go vertically through it, right through that vertex point, and it's going to be whatever the x point is. It's x equals 0 on this one. All right, let's take a look at a couple graphs here. So number 1, it says graph the function, then compare the graph of the function to the parent function, which is just the x squared. So I wrote down a table of values. Go ahead and put that down, and you can draw your x-axis and y-axis the way I drew it there for 1 and 2. So I'm going to do number 1, and then I'm going to let you try number 2 on your own. So again, we want to have a table of values just to plug in some numbers to get some points here on this graph. So if I want to plug in 0, 0 squared is 0, but then I would just have 5. So 0, 5 right here, red, 0, 5, that is going to be my vertex. Okay, that will be my vertex right there. Not necessarily because x is 0, but I know that that one's going to be the vertex of this one because we're going to be seeing that here in a minute. If I plug in 1, 1 squared is 1, and then 1 plus 5 would give me 6. If I put in negative 1 times negative 1 is positive 1, and then 1 plus 5 is 6 again. Notice again, this is why this is the vertex, because as we go 1 from 0 and negative 1 from 0, we're getting the same number. If you plug in 2, now we got 4. Here 2 squared is 4. 4 plus 5 is going to give me 9. Negative 2 times negative 2 is still 4, and that's going to be 9 as well. So now as we plot these points, if we say, okay, 0, 5, so 1, 2, 3, 4, 5, here is my vertex point, and if I go 1 this way, 1, 6, 1, 6 is going to be putting me just right here, and then if I go negative 1, I'm going to be at 6, it's going to be right there, and if I go to 2, we're going to be at 9, so 1, 2, and then you go 1, 2, 3, 4, 5, 6, 7, 8, 9 right at the top. And if I go to negative 2, we're also going to be up at the top. And so now there's a point, so we can just draw our U shape from this. Remember we talked about increasing and decreasing last time, so as you can see it's decreasing, and then now we're increasing, going up. So that's how we want to draw that. I'm going to just try not to make it a V shape, because V shapes are absolute value functions. This is a U shape, so it's quadratic. All right, now what would we say for this one? The only thing to say as we compare it here, I mean, we can compare it as far as it has the same axis of symmetry as the parent function, but it has shifted up. And what we're going to say is we're going to use the word translation as a vertical translation 5 units up. That's what we want to say for this one on comparing it to the parent function. All right, so I want you to go ahead and pause the video and try number 2. Do the same thing on number 2 and try to graph this one and write down what you should say as far as comparing it. And then play the video to see if you can check your answer. All right, so hopefully you do have a graph now for number 2. If you put in 0, we're going to just have it -3. If we put in 1, 1 squared, it's 1. 1 minus 3 is -2. -1 will be 1 minus 3 also. That's going to be also -2. If I plug in 2, that's going to be 4. 4 minus 3 is 1. If I plug in -2, it's going to also be 4 minus 3, which would be 1. And so at -3, 1, 2, 0, and -3. So that's 0, 0. I'm going to go down 3 units. Here's my vertex. When I go to 1 on the x, I'm going to go down to -2. When I go to -1, I'm going to -2. When I go to 2, I'm going to go to +1. When I go to -2, I'm also going to +1. And so there's our shape. And as you draw that, just try to make it a U shape. And just put arrows on the ends. Just go through the points and make arrows on the ends. And then for this one, the only thing we would need to say, it has the same axis of symmetry. The vertex, though, has moved. It's the same shape even as the parent function. It has that parent function pattern shape, in fact. Both of these do. As you can see, if we go 1 from this way, we're going to go up 1. 1 this way, we go up 1. If we go 2, we go up 4. Remember, that's 2 squared is 4. 1 squared is 1. If I went 3 this way, I know I'm going to go up 9 from here. It's not necessarily going to be 9 on the graph, on the numbers over here, but from the vertex, it has that same pattern. If you go 3, you're going to go up 9. If you go 4, you're going to go 4 squared, which you go up to 16, and so on. You have the same pattern on this one as well. And what we would say for this one, it's going to be a vertical translation, but this one's going to go down, and it's going to be 3 units. It's going to be not -3. You're not going to say -3. You're just going to say the number 3. So it's just vertical translation 3 units down, because down is the direction. That's the negative saying negative direction. So that's why we say down on that one. All right, let's move on to another one here. Let's take a look at this one. You don't need to write this down. Just watch it. We're graphing 4x squared plus 1. And so again, we're going to put a table of values out there and plug in our numbers to get the y coordinates as well, so we can plot the points. And as we plot the points, and we see the black one here is our parent function. So you can see that, x squared. The blue one is these points here plotted out. So you got your 0, 1, and there's your, when it's 1, when it's 2, it goes up to here. And you notice that this one is thinner or narrower because you have a 4 in front. So what we would say on this one is it's definitely going to stretch. It's stretching. It's getting narrower. If you like, you're putting your hands in the air and you're stretching it, or you're pulling it like a rubber band, you're stretching it. So we're going to say it's got a vertical stretch by that factor of 4. It also moved up 1, so we're going to say vertical translation 1 unit up. That's one of the things we're going to say there as far as comparing it to the graph of the x squared graph. The parent function, we're always going to most likely compare it back to the parent function. Sometimes we compare different ones. You know, we can compare it to a different one that's not the parent function, but most of the time it'll be compared back to the parent function. All right, so here we go with number 3 and 4. And if you want to pause the video and try 3 and 4 on your own, go ahead and do that, but I'm just going to go straight through 3 and 4. But it might be helpful for you to try this on your own and then check your answers with me. So as I put in 0 here, it's going to make this whole thing 0. 0 squared is 0, -3 times 0 is 0. The whole thing, 0 minus 2, is just going to give me -2. If I put in 1, it's going to be 1 squared is 1, and then times -3, so it's -3 minus a 2, that's going to give me -5. Plugging in -1 will do the same thing. That'll give me a +1, -1 times -1, and then times -3 is -3 minus 2, still -5. If I put in 2, 2 squared is 4, 4 times -3, that's going to end up giving me a -12 minus 2, that's a -14. If I put in -2, I'm going to get the same thing. I'll get a -2 squared is 4, 4 times -3 is -12, and minus 2 more is a -14. Okay, now if I'm doing a lot of this in my head, obviously, as I'm talking through this, but you can definitely, on a piece of scratch paper on the side over somewhere, you can definitely put this down on a piece of paper and make sure you don't make any little mistakes here with trying to get your Y numbers. Now I'm not going to probably be able to get these ones because they're pretty far down there. So I start with just 0, -2. So at 0 we go down to -2. And then 1, -5. So at 1 we're going to go down to -5. So there's 2, 3, 4, and 5. -1 we're going also down to -5. At 2 we're going down to 14, so I'm way off my graph here. So it is definitely getting thinner and narrower than the parent function, because the parent function would go 1 this way, 1 down, then 2 this way, and 4 down. It would be more out like this, but this one is definitely narrower. So as I kind of come up and then turn around and come down, arrows on the graphs there. So it's something similar to that. So there's the graph, and then what do we say about this one? Okay, well we could see since it's got the negative, it is opening down, so it's definitely going to have a reflection in the x-axis. That's one thing we're definitely going to say. It has an A number of 3, so since that 3 is more than 1, as you can see it's stretching, so it's going to stretch, not shrink. It's going to have a vertical stretch, and we would say by a factor, so the vertical stretch by factor of the number 3, by factor of 3. And then it also, we shifted down here, it moved down from its original position there, 0, 0, it just moved down 2 units. So it's going to be translation, but translation down. There we go. So it's also got a translation down. And for this one, we're going to say how many units. It went down 2 units. All right, that's what we want to say. Number 4, as we start to work through this one. So I plug in 0 again. It's going to make it 0 times a half is 0. And it's just going to give me the -4. So again, there's my vertex. This will be my vertex. And then 2, that's going to give me 4 here. Now notice I use 2's and 4's here because I have a 1/2. So when I plug in a 2, I'm going to get a nice neat number. So I'm going to get 2 squared is 4. It'll be the same thing when I do -2. -2 squared is also 4. And then half of 4 is 2. 2 minus 4 is -2. So we're going to get -2 for both of those. If you plug in 4 or -4, here you're going to get 16. And half of 16, here when you multiply 16 and a half of 16 is 8, and 8 minus 4 is 4. So we're going to get 4's for both of those. Again, you might want to do some work on a scratch paper. I'm just not doing it to save some time. But that's what you should be doing. You're just plugging the number in and then working it out according to order of operations. So 0, -4, as we plot these points. 0 and then 1, 2, 3, 4. We're down here. 2, -2. So I go to 2, down to 2, down 2. Go to -2, we're also going down 2. When I go to 4, so 1, 2, 3, 4, I'm going to be up 4. 1, 2, 3, 4, right to here. And when I go to -4, I'm also going to be up 4. So this one is opening up, as we can see where these points are. That's positive. It's a positive 1/2 in front of the x squared. That x squared term is positive. And so now we come up, put arrows on the ends of these. Always put your arrows on the ends because it shows it keeps going up and fanning out each way. So we can see, according to this, the parent function, if I was to do the parent function pattern from here, 1, 1, and then 2, I go 4, 1, 2, 3, 4, which would be inside of this. So this is definitely wider. It's wider because this is a 1/2. It's between 0 and 1. So wider means shrink. So we're going to have a shrink on this one. There is no reflection. It's still opening up. So no reflection, but it will have a shrink on this one because of the 1/2. And we would just say that as well. So shrink by factor of 1/2. And then also it moved down. It went down 4 units right here. So we want to say that also it moved down. It not just moved down, but the translation word, translation down. So it has a translation down. And we can say that that is down 4 units. So we just put 4 units. All right, let's move on to our next one. And before we get to our next problem, let's look at our joke of the day. It says, what do you call a rabbit who is really cool? What do you call a rabbit who is really cool? Well, we have a rabbit at our house. His name is Chuck Norris, and he is really cool. But according to this, what do you call a rabbit that is really cool? You call him a hip hopper. He is a hip hopper. All right. Remember, it used to be a word we always say way back in the day. You might not say the hip anymore, but when somebody's hip, that means they're really cool. So he's a hip hopper. All right, so here we go into a couple different pages. On page 252, you'll see a vocabulary word or a little thing there, which is zero of a function. What is a zero of a function? What do they mean by a zero of a function? Well, this is just one way to basically say the answer of a function, the answer of some equation. So basically when they're talking about a zero of the function, they're saying this: a zero of a function is an x-intercept of the graph of the function. So remember, these are U-shaped graphs. Where does this cross the x-axis? That is the zero of the function. If we go back to the ones that we just graphed here, this one doesn't have any zeros. It doesn't cross the x-axis at all. But this one crosses the x-axis in these 2 places. Those 2 places would be the zero of the function. Let's see back on this one here. Number 1, there is no zeros of this function because it doesn't cross the x-axis. We would say there's no real zeros on that one. But this one does cross the x-axis in 2 places, and this one does have 2 zeros of the function. So basically the zeros of the function is where it crosses the x-axis. It is the x-intercepts of the function. But it's also, if we were to set this equal to 0, okay, if we put the m of x a 0, gave the m of x a 0, basically if we put 0 for y and solve for x, that's going to give us the zeros of the function. Because when we're on the x-axis, that is when y equals 0. We don't see 0 over here, but we could put a 0 over here and then figure that out. Okay? So that's essentially what we're doing, is we're going to make the m of x or the g of x or whatever the function is or whatever the y says, we're going to make that into 0, and then we're going to solve our equation. And we've solved equations like this already with factoring. So we learned how to factor already, and that's what we're going to basically do on these. Find the zeros of the function. Now we can graph them. Now I can use a graphing calculator, and we can graph them and try to locate the zeros of the function that way. But the way we want to actually do it here without graphing, if you don't have a graphing calculator, if that's not available to you, then you would just make this into this y here. So for number 5 on 254, first thing we're going to do is we're going to make that y into 0. We're going to give it a 0. We're going to substitute 0 in for the y. So that way we're on the x-axis. And then where is the solution? What would x be on the x-axis? That's what we do by solving this. Well, this right here, what we can see is we can factor out a negative because we want to do that first. We've done that before. Factor out a negative because we need to see this as just a positive x squared. So now it's just x squared minus 1. And so now we would just see a difference of two squares here. So x squared minus 1 is a difference of two squares. You can factor the two binomials. Still have the negative in front here. X minus 1, x plus 1. And now we're ready to use the zero product property. We've done that one in the previous chapter. So zero product property. Now we don't need to worry about this negative because there's no x that was factored out. The x's are only inside the parentheses, so I just need to do x minus 1 is equal to 0 and x plus 1 is equal to 0. We add 1 for this one, we subtract 1 on this one, and so you can see x equals 1 and x equals negative 1. Now if I was to graph this function, actually graph it on a coordinate plane here, you could see here's what the graph would look like. Okay, it would be, there's my 1, it's shifted up 1, it's opening down because of negative. It has the same shape as the parent function because it's just a 1 in front of x squared. So 1 this way, we go down 1. 1 this way, we go down 1. 2 this way, we go down 4, and so on. And you can see here are the x-intercepts. The x-intercepts right there is 1 and negative 1. That's the x-intercepts. That's the solutions. Those are the zeros of the function. All right, I'm going to do number 8, and then I'm going to have you try number 6 and number 7 on your own. So number 8, p of x. So what we're going to do here is, if we're trying to find the zero of the function, we're going to make p of x, substitute 0 in for the p of x. Just change that to 0. And then we want to solve for x. We solve for it by using our factoring. And again, I'm going to factor out, here I already did it, factoring out a negative of these two terms now gives me 9x squared minus 1, which that's also a difference of two squares. 9x squared is a perfect square term. The minus 1 is, it's got a difference. And so we're going to factor it to two binomials. Break the 9x squared apart to 3x and 3x, and then the 1 becomes 1 and 1, 1 plus and 1 minus. Again, the negative is still on the outside. We don't need to worry about it because there was no x factored out. The x's are only inside the parentheses. So as we use the zero product property and solve, so for the first one here, 3x minus 1 equals 0. Add 1 to both sides. We're going to see it's 3x equals 1. So if I divide by 3, our first answer could be 1 over 3, 1/3. And then this over here, our other one, the 3x plus 1, set that equal to 0. And we're going to subtract 1 from this one. And so now we have 3x equals negative 1. And then divide by 3. So for this one, x is going to equal a negative 1/3. If I was to do a graph for this one, as you can see here, so if I did a graph, I did my graph, but then I also graphed it on the graphing calculator. You can see how this would be the graphing calculator here in red. I'm in kind of blue, so it's very close. So there's my graph right there. This is the graphing calculator of it. And you can see where the x-intercepts are. Maybe you see them a little bit better here. Here's 1, here's negative 1, so we're inside there. We can't really tell. And this is why you really want to do it this way, because sometimes when you graph it, if you're graphing it freehand, it's very hard to tell what those x-intercepts are because it's not a nice, neat point there. On the graphing calculator, you could tell a little bit more clearly, especially on the one I was just showing you, that Desmos one, because you can click on the graph and it will highlight those points for you and show you exactly what they are. Alright, so go ahead and pause the video and find the zeros of number 6 and number 7 of those two functions, and then play it to see if your answers are correct. Alright, so hopefully you do have an answer now for number 6, number 7. Let's just check to see if your answers are correct. So for this one, number 6, you should have got 2 and negative 2 for answers. So if you didn't get those two answers, you definitely want to look through this. I factored out a negative 4 from these two. And then we have an x squared minus 4. That's our difference of two squares. We factor it to x plus 4, x minus 4. I don't need to worry about the negative 4 on the outside because there's no x there. I only need to set the ones where the x's are equal to 0 using zero product property. And so that gives me my positive 2 and negative 2. Number 7. Our answer for number 7 here should be an 8 and a negative 8. This one you just need to factor out the negative and you get x squared minus 64. There's another difference of squares. So you get x minus 8, x plus 8. And so that way you just set those two equal to each other, equal to 0, not equal to each other. Set both of them equal to 0 using zero product property. Solve for x by adding 8 and subtracting 8. So that's what your answer should be. So not too difficult, but just remember when it says find the zeros, it just means to plug in. Now it also might say find the x-intercepts. What if it says that? Well, if it says find the x-intercepts, you means do the same thing. Plug 0 in for your y or for the function notation or whatever function notation that might be. This is n of x, p of x. A lot of times you see f of x, g of x, those kind of things. So there's different ways of being able to say find the solutions of the function. So if it's actually already got a 0 here, if it already is in this form, it'll probably just say solve the quadratic function. But if it's in more of a function notation with a y or a function notation like this, it'll probably ask you to find the zeros or find the x-intercepts or even find the roots. Roots is another one that it might be. So you can also maybe write that down. Roots is another way they also say to find the zeros. So there's really three ways. X-intercepts is one way, zeros is another way, and then roots is another way. They might ask you in this form when it's more of in a function notation and they want you to solve it for x, and they want you to do this kind of process. They're going to say x-intercepts, zeros, or roots. Find them. Find the roots, find the zeros, find the x-intercepts of the function. It all means to do the same thing. Alright, let's move on to 9 and 10. Just says to sketch a parabola with the given characteristics. And I'm going to have you try these and see if you can maybe do this on your own. Number 9, the parabola opens down. So you know you're going to draw one opening down. And the vertex is at 0, 5. So you just draw a coordinate plane, put your vertex 0, 5 opening down, and that's all you need to do. This one, number 10, lowest point of the parabola is at 0, 4. So go to 0, 4. That's the lowest point, which means if you know it's the lowest point, it's going to be having to open up like that. So go ahead and try to draw two of those, and I'll just show you what I have as a sample. So hopefully you paused the video now. You did 9 and 10. You just drew a function for each of these. And it says sketch a parabola. Remember, that's the name of these. We can call these parabolas. These U-shaped graphs, the graphs of the quadratics, are called parabolas. So this is just a sample answer. Yours is not going to be exactly like this, but it should definitely have your vertex here at 0, 5, and it should be opening down from that way. As long as you got that, that's perfectly fine. And for this one, again, this is just a sample answer, but you should have your vertex at 0, 4. Here's 0, 4. This is going by 2, by the way. This is 2, 4, 6, 8. So 0, 4 is there, and it's just opening up from there. Okay. It doesn't say anything about how wide or how narrow to make it. So as long as it's just opening up, that's all you need to do. All right, we're just going to look at our last problem. Now this last problem is going to be more of a word problem, more of a situation problem, more like even a real life situation problem. Let's take a look at this example before we get to number 11, because this one actually has a picture on it. I think it'll make a little more sense. This one says the function f of t equals negative 16t squared plus s of 0. In this little subscript of 0, s of 0 here. This would be the same thing we're going to use on number 11. It says it represents the approximate height in feet of a falling object t seconds after it is dropped from an initial height s of 0 in feet. So our problem says exactly the same thing. It says this situation is saying that an egg is dropped from a height of 64 feet. That's the situation. We have a different situation on ours. I think our situation on this one says a tennis ball is dropped from a height of 400 feet. Okay, so, but all the same stuff up here. So you're on top of maybe this building, you're dropping an egg on this example, or you're dropping a tennis ball on our example that we're going to do. It says after how many seconds does the egg hit the ground? Okay, well the ground would be when height would be 0. Right now you're at 64 feet up here, the ground would be 0. So when we talk about the height of the ground, that's 0. That's your f of t. The s of 0 is the initial height, s of 0, and the initial height is 64 feet on this one. It's going to be 400 feet on ours. So all you have to do is just plug these things in. 0 for f of t, 64 for s of 0, and then solve. Find the zeros is what you're looking for. You're finding the zeros of the function, and that would give you the how many seconds. That would be solving for t, because t is the time, t seconds after it's dropped. It says how many seconds does the egg take, to hit the ground. So we are looking to solve for t. And then on this one it says, suppose the initial height is adjusted by k feet by some number. We're actually going to have a number. So if that height's adjusted, if your height gets adjusted to be a higher height, where you're up even higher than this, it's going to take longer to get there. The t will be a bigger number. If the height gets down lower, if now you're down somewhere in here, less than 64, it's going to not take as long to hit the ground. All right, let's take a look at our example number 11 with this tennis ball. The tennis ball falls from a height of 400 feet. Everything else is the same, our same equation right here, this function. And it says after how many seconds does the tennis ball hit the ground? So remember, the ground here is going to be, the height of the ground is 0. So f of t is going to be 0. And for 400, that's going to be our s of 0. Our initial height, 400, is our initial height. That's what it says here. Initial height is the s of 0 in the function. And the initial height here says 400. So we're just going to plug those two things in. 0 here and 400 goes here. And now it looks like this. 0 equals negative 16t squared plus 400. And now we're going to find the zeros just like we were finding them earlier. I'm going to factor out negative and a 16. 16 does go into 400. So when I factor a negative 16 out, I get t squared minus 25. That does give me a difference of 2 squares, which I can factor to 2 binomials. So negative 16 is still out in front, but now I have t minus 5, t plus 5. I don't need to worry about that negative 16 because it doesn't have a variable on it. It's just a number. So I just set those two equal to 0. So t minus 5 is going to become t equals 5. Now I didn't show you the setting equal to 0 part. We did that earlier, but we know we're going to get 5 from this one. We're going to get negative 5 from the other one. That's using zero product property to get that. And so now if we have t equals 5 and t equals negative 5, that's two different numbers. Which number should we use? Well, one number would make sense. The other number shouldn't make sense. Again, look at the question. After how many seconds does the tennis ball hit the ground? Is it after 5 seconds or after a negative 5 seconds? Well, negative 5 seconds doesn't make any sense. It says, since time cannot be negative, we can only use positive 5. So we're just going to use 5. It's 5 seconds. So the answer to this question, after how many seconds does the tennis ball hit the ground? It is 5 seconds. All right, letter B says, suppose the initial height is decreased by 384 feet. All right, so we're going to decrease our initial height from 400 by 384, not to 384. We're decreasing it by that amount. So we're going to do this. We're going to subtract. Our initial height, s of 0, is going to be 400 minus 384. So that's going to now be an initial height of 16. That's our initial height now for this one. It says, after how many seconds does the ball hit the ground? So again, the ground means the f of t is equal to 0. So I want you to pause the video now, and I want you to try to find the answer for this one, for letter B. So use the same function where you're going to plug in 16 for s of 0, and the 0 still goes in for f of t. So the only difference now would be the 400 is now a 16 here. So go ahead and solve that one and see if you can get your answer correct on here. Alright, so hopefully you pause the video on this last one, and now you have an answer for how many seconds does it take for the ball to hit the ground. So it should have gotten 1 second. That's what your answer should have been. If you did that, if you got 1 second, then you must have done this correctly. If you got something different, let's take a look. It says when you plug in 0 here, you got your negative 16t squared, and we're going to put plus 16 for the initial height. We're factoring out the 16 again, the negative 16 in fact, getting t squared minus 1. So you had to factor out the negative and the 16 to get this difference of squares. It factors to t minus 1 and t plus 1. And so using zero product property for just those two where the t's are, we're going to get t is equal to 1 and t is equal to negative 1. But again, you can't use the negative because you can't have, again, time cannot be negative, so we can only use positive 1. So that's where we're getting 1 second from. Alright, so that concludes our lesson here on 8.2. And I'll see you again on 8.3 where we're going to add a little bit more to our quadratic functions here. So I'll see you guys then. Have a great rest of your day.